Imagine a dark world drifting silently through space. A small, jagged asteroid, no larger than a mountain, slowly orbiting the Sun, billions of kilometers from Earth. For billions of years, it remained untouched, a fragment left over from the chaotic birth of our solar system, older than the planets themselves. But scientists suspected that this tiny world might hold something extraordinary. Not gold, not rare metals, but something far more important. Clues about the earliest chemistry of the solar system. Clues about how water may have reached Earth. And perhaps even the ingredients that helped life begin. So NASA launched a spacecraft across millions of kilometers of space, not to land on this asteroid, but to touch it briefly, collect a sample of its surface, and bring that material back to Earth. When the capsule finally returned and scientists opened it, what they found inside Bennu shocked them. This is Bennu, the asteroid NASA brought back to Earth, and the ancient secrets hidden inside it. Before we begin exploring this mysterious world, subscribe to Theories Before Sleep, where we slowly uncover the quiet mysteries of the universe. Long before the Earth had oceans, before the Moon existed, before the planets even settled into the stable orbits we know today, the solar system was a violent place. Dust and rock filled the space around the newborn sun. Billions of tiny particles collided constantly, clumping together, breaking apart, and forming larger bodies in an endless cosmic construction site. Some of these bodies grew into planets. Others never got that chance. They remained as fragments of the early solar system, primitive objects that preserved the chemistry and structure of that chaotic era. One of those fragments is Bennu. At first glance, Bennu does not look particularly impressive. It is not a giant asteroid like Vesta. It does not have dramatic metallic cliffs like Psyche. And it certainly does not shine brightly in telescopes. Bennu is small, very small. The entire asteroid is only about 500 meters wide, roughly the height of the Empire State Building if it were laid on its side. If you stood on its surface, you could walk from one side to the other in less than 20 minutes. Yet despite its small size, Bennu has become one of the most scientifically important objects ever studied in space. Because Bennu is not just a rock, it is a time capsule, a preserved remnant from the earliest days of our solar system, holding materials that formed more than 4.5 billion years ago. And unlike most asteroids, Bennu has delivered some of those materials directly to Earth. But to understand why that matters, we first need to understand what Bennu actually is. A pile of rubble. When people imagine asteroids, they often picture something like a solid mountain floating through space, a giant chunk of rock drifting silently around the sun. But Bennu is not like that. It is something far stranger. Bennu is what scientists call a rubble-pile asteroid. That means it is not a single solid object at all. Instead, Bennu is a loose collection of rocks, boulders, gravel, and dust, all held together only by its extremely weak gravity. Imagine taking thousands of pieces of broken stone and letting them slowly gather together in space. That is essentially what Bennu is, a floating pile of debris. In fact, the gravity on Bennu is so weak that if you tried to jump, you might never come back down. The escape velocity of the asteroid is only about 20 centimeters per second, slower than a casual walking pace. A gentle push could launch a pebble completely off the asteroid and into space. Standing on Bennu would feel nothing like standing on Earth. You would not feel your weight pressing into the ground. Instead, every movement would have to be careful and controlled. One wrong step could send you drifting upward. And yet somehow, despite this fragile structure and weak gravity, Bennu has remained intact for millions of years. That alone is remarkable. But Bennu's structure also hints at its violent past, because Bennu itself did not form alone. It is the broken child of something much larger. The destruction of a parent asteroid. Billions of years ago, somewhere in the asteroid belt between Mars and Jupiter, a much larger asteroid existed. This ancient body may have been tens of kilometers wide, possibly even larger. But the asteroid belt is not a peaceful region. Collisions between asteroids happen constantly over cosmic timescales. Eventually, that parent asteroid experienced a catastrophic impact, a collision so powerful that it shattered the entire object into countless fragments. Some fragments became large asteroids, others became clouds of debris, and over time, gravity slowly gathered some of those fragments together again. That process created Bennu. Instead of forming as a single solid rock, Bennu assembled from the broken remains of its parent asteroid, like a puzzle made of shattered pieces. The result is the strange diamond-shaped object we see today, a spinning mound of rubble floating through space. But Bennu did not remain in the asteroid belt. Something slowly nudged it toward Earth. The invisible push. In space, even the smallest forces can slowly change the paths of objects. One of the most subtle forces acting on asteroids like Bennu is something called the Yarkovsky effect. It sounds complicated, but the idea is surprisingly simple. During the day, sunlight heats the surface of the asteroid. When night arrives, that heat slowly radiates back into space as infrared energy. But this radiation does not leave evenly. Because the asteroid rotates, the warmest part of the surface releases heat slightly after sunset, and that escaping heat acts like a tiny thrust, almost like the asteroid has invisible rocket engines firing very gently. Each day the push is incredibly small, almost nothing. But over millions of years, those tiny pushes add up. They slowly alter the asteroid's orbit, gradually moving it closer to the inner solar system. This is exactly what happened to Bennu. Over millions of years, the asteroid drifted away from the main asteroid belt and eventually entered an orbit that crosses Earth's path around the Sun. Today, Bennu is classified as a near-Earth asteroid. It circles the Sun once every 436 days, passing relatively close to Earth during its orbit. Close enough, in fact, that scientists began paying very close attention to it. Because Bennu is not just scientifically interesting, it is also potentially dangerous. A small chance of impact. When astronomers track near-Earth asteroids, they carefully calculate their future paths. For most asteroids, the answer is simple. They will never hit Earth. But Bennu is different, because its orbit occasionally brings it close to our planet, close enough that Earth's gravity can slightly alter its trajectory during each flyby. These gravitational nudges make Bennu's long-term path extremely difficult to predict. Scientists have calculated the asteroid's orbit far into the future, running millions of simulations to understand every possible outcome. The results are reassuring, but still fascinating. There is a very small chance that Bennu could impact Earth sometime in the distant future. The most notable potential date is September 24th, 2182. Even then, the probability is extremely low, about 1 in 2,700. That means there is more than a 99.96% chance Bennu will miss Earth entirely. But the possibility was enough to make Bennu one of the most carefully studied asteroids in history. Because if scientists ever needed to learn how to deflect an asteroid, Bennu would be a perfect test case. And that was one reason NASA decided to visit it. But the most important reason was something else. Bennu might contain the original building blocks of life. The carbon clue. When astronomers studied Bennu with telescopes from Earth, they noticed something unusual about its surface. It appeared extremely dark, darker than coal. This darkness suggested that Bennu belongs to a group of asteroids called carbonaceous asteroids. These are some of the most primitive objects in the solar system. They are rich in carbon compounds, organic molecules, and water-bearing minerals. In other words, the kinds of materials that may have played a crucial role in the origin of life. Billions of years ago, when Earth was still forming, countless asteroids and comets bombarded the young planet. Many scientists believe these impacts delivered large amounts of water and organic chemicals to Earth's surface. Without those materials, life may never have appeared. So studying Bennu could help answer one of the biggest questions in science. Where did the ingredients for life come from? But telescopes can only reveal so much. To truly understand Bennu, scientists needed something much more powerful. They needed samples, real pieces of the asteroid itself, and that meant sending a spacecraft across millions of kilometers of space to collect them. The beginning of a mission. In September 2016, NASA launched a spacecraft called OSIRIS-REx. The name may sound complicated, but it actually describes the mission's goal. OSIRIS-REx stands for Origin Spectral Interpretation Resource Identification Security Regolith Explorer. In simple terms, the spacecraft had one primary mission: travel to Bennu, study the asteroid in detail, collect a sample from its surface, and bring that material back to Earth. No spacecraft had ever attempted such a mission to a carbon-rich asteroid before. The journey would take 2 years. During that time, OSIRIS-REx traveled more than 2 billion kilometers, performing precise maneuvers to match Bennu's orbit around the Sun. Finally, in December 2018, the spacecraft arrived, and what it found surprised everyone, because Bennu did not look the way scientists expected. Instead of a smooth surface covered in fine dust, the asteroid was covered in giant boulders. Sharp, jagged rocks everywhere. Landing on such a surface would be far more difficult than planned. In fact, it almost made the entire mission impossible. But the real surprises were still waiting. Because Bennu was not just a quiet pile of rocks drifting through space. It was active, alive with subtle motion. Particles were erupting from the surface. Tiny rocks were lifting into space before falling back down again. It was something scientists had never seen before on an asteroid this small. And it suggested that Bennu still held secrets deep within its rubble-filled interior. secrets that scientists were only beginning to uncover. When the OSIRIS-REx spacecraft finally arrived at Bennu in December 2018, scientists expected to find a relatively calm and predictable asteroid. The mission had been carefully planned for years. Engineers believed Bennu would have a surface covered in fine dust and sand, material loose enough for the spacecraft to briefly touch and easily collect a sample. Everything about the mission depended on that assumption. But almost immediately after entering orbit, Bennu began to surprise everyone. Because the asteroid was not quiet, it was active. And the first sign of that activity came in the form of something completely unexpected: tiny eruptions of rock. The asteroid that throws rocks. Only a few weeks after OSIRIS-REx arrived at Bennu, cameras aboard the spacecraft began detecting small particles drifting near the asteroid. At first, scientists were confused. Particles were appearing in the images where none had been seen before. Then they realized something remarkable. The particles were not arriving from space. They were coming from Bennu itself. Small rocks were being launched from the asteroid's surface. Some particles were tiny, only a few centimeters across. Others were slightly larger. The spacecraft watched as these fragments lifted off the surface, drifted slowly through the weak gravity, and eventually fell back down again. In some cases, the particles even escaped the asteroid completely. This was astonishing. Before OSIRIS-REx, no one had ever observed an asteroid actively ejecting material into space like this. Asteroids were supposed to be inert objects, cold, silent, geologically dead. Yet Bennu was behaving almost like a miniature comet, but without the ice jets or gas plumes normally responsible for such activity. So what was causing the asteroid to throw rocks into space? Scientists began investigating several possible explanations. A planet under stress. One possible cause was temperature. Bennu experiences extreme temperature changes every single day. During the asteroid's daylight hours, sunlight heats the surface to around 120 degrees Celsius. But when night falls, the temperature drops rapidly. This dramatic expansion and contraction puts enormous stress on the rocks covering the asteroid. Over time, the repeated heating and cooling can cause boulders to crack and fracture. Eventually, pieces may break off and be launched upward. But temperature stress alone could not explain all the particle events. Some of the ejections appeared more energetic than simple cracking. Another possibility involved tiny impacts. Bennu is constantly bombarded by microscopic meteoroids. Even small grains of dust moving at high speeds can strike the surface with enough force to kick up debris. In Bennu's extremely weak gravity, those fragments can easily be launched into space. Yet even this explanation seemed incomplete. The pattern of particle ejections did not fully match what scientists expected from impacts alone. There was likely something else happening, something deeper inside the asteroid. Bennu's spinning shape. When OSIRIS-REx began mapping Bennu in detail, scientists quickly noticed another strange feature. The asteroid was not shaped like a potato or an irregular rock. Instead, Bennu had a very specific form. It looked almost like a spinning top. The asteroid bulges around its equator, forming a ridge of material circling its middle. This shape is not random. It is caused by Bennu's rotation. The asteroid spins once every 4.3 hours. As it rotates, the centrifugal force pushes loose material outward toward the equator. Over millions of years, this process slowly reshaped the asteroid. Rocks and dust migrated downhill toward the equatorial ridge, gradually building the diamond-like shape seen today. But Bennu's rotation may also be connected to the particle ejections, because the asteroid is slowly spinning faster, and the reason for that acceleration is something surprisingly subtle: sunlight. The power of light. In space, sunlight can do more than simply warm an object. It can actually change the way an asteroid spins. This happens through a phenomenon called the YORP effect. As sunlight strikes the surface of an irregular asteroid, some of the energy is absorbed and later re-emitted as heat. But because the asteroid's surface is uneven, this re-emission does not happen equally in all directions. Some areas release slightly more energy than others, and over time, this uneven radiation creates a tiny torque, a gentle twisting force. The effect is incredibly small, but over thousands or millions of years, it can significantly alter an asteroid's rotation. In Bennu's case, the YORP effect is slowly increasing its spin rate. Measurements from OSIRIS-REx confirm that Bennu's rotation is accelerating by about 1 second every 100 years. That may not sound like much, but over long periods of time, it can dramatically reshape the asteroid. As Bennu spins faster, material near the equator experiences greater outward force. Eventually, rocks may lose their grip on the surface. When that happens, they can slide or even be flung off into space. This may explain some of the particles observed around Bennu, but it also suggests something even more dramatic. If Bennu continues spinning faster and faster, the asteroid may eventually begin to break apart, slowly shedding pieces of itself into space. A surface covered in boulders. As OSIRIS-REx continued mapping the asteroid, another surprise emerged. The surface of Bennu was far rougher than expected. Before the mission launched, scientists predicted that Bennu would have large areas of smooth terrain covered in fine-grained regolith. Instead, the asteroid was littered with enormous boulders, some of them larger than houses. Sharp, jagged rocks covered almost the entire surface. Safe landing areas were extremely rare. In fact, the spacecraft's original sample site had to be abandoned. There simply was not enough open space for the sampling arm to safely reach the surface. Mission planners were forced to search the asteroid for a new location. Eventually, they selected a small crater called Nightingale. It was one of the few places on Bennu where relatively fine material appeared to exist. But even this site was only about 8 meters wide, barely larger than a few parking spaces, and it was surrounded by dangerous boulders. Landing there would require extraordinary precision. A close look at Bennu's rocks. While searching for a safe sampling site, OSIRIS-REx began analyzing the asteroid's surface in incredible detail. And the composition of Bennu's rocks revealed something remarkable. Many of the boulders appeared extremely fragile. Some looked as if they might crumble at the slightest touch. Spectral analysis suggested these rocks contained large amounts of clay minerals. Clay forms when water interacts with rock. But Bennu itself does not have liquid water today, which means these minerals must have formed somewhere else, most likely inside Bennu's parent asteroid billions of years ago. At that time, water circulating through the larger body may have chemically altered the rocks, producing hydrated minerals and organic compounds. When the parent asteroid was later destroyed by a massive collision, fragments of those altered rocks eventually reassembled into Bennu. That means Bennu carries within it pieces of an ancient world that once contained liquid water, even though the asteroid itself is now dry and airless, and those hydrated minerals made Bennu incredibly valuable to scientists because they might also contain preserved organic molecules, the same types of molecules that may have contributed to life on Earth. The moment of truth. After months of mapping, analyzing, and planning, the OSIRIS-REx team finally prepared for the most critical phase of the mission, the sample collection. Unlike traditional landers, OSIRIS-REx was never designed to land permanently on Bennu. Instead, it would perform a maneuver called touch and go, or tag. The spacecraft would slowly descend toward the asteroid, extend a long robotic arm, briefly touch the surface for just a few seconds, fire a burst of nitrogen gas to stir up loose material, capture that material inside the sampling head, and then immediately retreat back into orbit. The entire contact with the surface would last less than 10 seconds. But those 10 seconds would determine the success or failure of the entire mission. Because if the spacecraft missed its target, there might not be enough fuel to try again. Years of work depended on a moment shorter than a television commercial. And the surface of Bennu was far more dangerous than anyone had anticipated. Large boulders surrounded the tiny Nightingale crater. If the spacecraft touched one of them, it could damage the sampling arm, or even destroy the mission entirely. Despite these risks, the team decided to proceed. The maneuver was scheduled for October 20th, 2020. On that day, OSIRIS-REx began its slow descent toward Bennu. And as the spacecraft approached the surface, something even more unexpected happened. The ground beneath the sampling arm behaved nothing like solid rock. It behaved like liquid. But the full story of that moment and what happened when the spacecraft finally touched Bennu would reveal just how strange this asteroid truly is. On October 20th, 2020, the OSIRIS-REx spacecraft began one of the most delicate maneuvers ever attempted in space exploration. For nearly 4 years, the mission had traveled across billions of kilometers, studied the asteroid Bennu in extraordinary detail, and carefully selected the safest place to collect a sample. Now everything depended on a brief moment, a single touch. The spacecraft was slowly descending toward the surface of Bennu, moving at less than 10 centimeters per second, about the speed a human hand might drift forward in slow motion. Every movement had been planned months in advance, but as the spacecraft approached the asteroid, something became immediately clear. Bennu's surface did not look solid. It looked soft, much softer than anyone expected. The surface that wasn't solid. As OSIRIS-REx descended closer and closer to the Nightingale crater, its navigation cameras captured the asteroid's surface in extraordinary detail. The spacecraft could see individual pebbles, small rocks, loose dust. Everything looked fragile and loosely packed. But what no one realized yet was just how loosely held together that surface truly was. When the spacecraft's robotic arm finally touched Bennu, something astonishing happened. Instead of striking solid ground, the sampling head began sinking. The arm pushed straight into the surface as if it had plunged into a pile of powder. Large rocks shifted aside. Dust and debris erupted outward in slow motion. The spacecraft sank nearly half a meter into the asteroid. Scientists, watching the data later, compared the moment to landing in a pit of ball bearings or loose sand. The ground offered almost no resistance. For a brief moment, the spacecraft was essentially floating inside Bennu's surface. And that was far more dangerous than expected, because the mission was never designed to land. If the spacecraft had continued sinking, it could have tipped over or become trapped. But fortunately, the sampling system activated exactly as planned. The nitrogen burst. The sampling mechanism aboard OSIRIS-REx was called TAGSAM, short for Touch and Go Sample Acquisition Mechanism. Instead of digging into the ground with drills or scoops, TAGSAM used a much simpler technique: a burst of compressed nitrogen gas. As soon as the sampling head touched Bennu's surface, a small canister released nitrogen gas directly into the loose regolith. The gas stirred up dust, pebbles, and fragments. Those particles were then captured inside the collection chamber of the sampling head. The entire process took only a few seconds. Then the spacecraft fired its thrusters and slowly backed away from the asteroid. At first, mission controllers did not know if the maneuver had succeeded. Signals from the spacecraft took over 18 minutes to travel from Bennu to Earth. That meant the entire operation had already finished long before the team received confirmation. When the first images finally arrived, the room erupted with excitement. The pictures showed a cloud of debris exploding outward from Bennu's surface. Dust and rocks were drifting through space all around the spacecraft. It looked like a miniature explosion, but it was exactly what scientists hoped to see. The gas burst had clearly stirred up large amounts of material, and much of it had likely been captured. Yet the surprises were not over, because the spacecraft had collected far more material than expected. Too much of a good thing. The mission required only 60 grams of asteroid material to be considered successful. That is about the mass of a small chocolate bar. But when engineers examined the spacecraft's images, they noticed something strange. Particles were escaping from the sampling head. Small rocks were drifting away from the spacecraft. At first, this seemed alarming, but then scientists realized what had happened. The sampling head had collected so much material that it could not fully close. Pebbles were wedged inside the mechanism. Some fragments were literally spilling out into space. The spacecraft had gathered far more than the required sample mass, possibly hundreds of grams of Bennu's surface material. This was incredible news, but it also created a new problem. If too many particles escaped, some of the sample could be lost. Engineers decided to skip one of the planned measurement maneuvers and immediately store the sample inside the spacecraft's sealed return capsule. This ensured that the precious asteroid material would remain safely contained for the journey back to Earth. And that journey would take nearly 3 years. The long trip home. After securing the sample, OSIRIS-REx continued orbiting Bennu for several months. During that time, the spacecraft conducted additional observations of the asteroid. But the mission's most important objective had already been accomplished. In May 2021, the spacecraft fired its engines and began the long journey back to Earth, carrying with it the largest sample ever collected from an asteroid. The spacecraft itself would never land. Instead, it would release a small return capsule containing the Bennu sample as it flew past Earth. That capsule would plunge through the atmosphere and parachute down to the surface. Inside, it would be material older than Earth itself. Fragments of rock that formed in the earliest moments of the solar system. But before the capsule even returned, scientists had already learned something profound about Bennu, because the asteroid's surface had revealed a fundamental truth. Bennu is not just fragile, it is barely held together at all. A world of floating rocks. The moment OSIRIS-REx touched Bennu revealed something surprising about rubble-pile asteroids. Their surfaces may not behave like solid ground. Instead, they can behave more like fluidized material. The asteroid's gravity is so weak that even small forces can rearrange its structure. When the spacecraft touched the surface, the material simply flowed aside. Large rocks shifted as if floating. Dust clouds expanded outward. The asteroid behaved almost like a granular liquid. This discovery changed how scientists think about small asteroids. Many rubble-pile asteroids may have interiors filled with empty spaces, loose rock fragments barely touching each other. Instead of solid bodies, they may resemble cosmic sand piles, and that has important implications for planetary defense. If an asteroid like Bennu were ever on a collision course with Earth, deflecting it might not be as simple as pushing on a solid object. Applying force to a loosely packed asteroid might cause it to absorb the impact differently, or even break apart. Understanding these structures is critical for designing future asteroid deflection missions. But Bennu was also revealing something else, something hidden inside its rocks, something much older than the asteroid itself. Ancient chemistry. Even before the sample returned to Earth, OSIRIS-REx instruments had already detected intriguing chemical signatures on Bennu's surface. Spectrometers aboard the spacecraft identified hydrated minerals. These minerals contain water molecules trapped inside their crystal structures. That means water must have once interacted with the rocks that eventually formed Bennu. But Bennu itself is far too small to have ever supported liquid water internally. The water interaction must have happened inside Bennu's much larger parent asteroid billions of years ago. At some point in the early solar system, that parent body likely contained internal heat, possibly from radioactive decay or ancient collisions. That heat allowed water ice inside the asteroid to melt temporarily. The liquid water then reacted with surrounding minerals, chemically altering the rock. When the parent asteroid was later destroyed by a massive impact, fragments of those altered rocks eventually reassembled into Bennu. In other words, Bennu carries pieces of an ancient water-rich world, a world that existed billions of years ago. And that raises a fascinating possibility. Those ancient rocks might also contain complex organic molecules, the chemical ingredients that can form amino acids and other building blocks of life. But scientists would need to wait until the sample returned to Earth to know for certain. A capsule from the past. The return capsule carrying Bennu's sample was designed to survive an intense journey. As it entered Earth's atmosphere, temperatures would reach nearly 3,000 degrees Celsius. The heat shield would protect the interior from that inferno. After slowing down, parachutes would deploy, gently lowering the capsule to the ground. The landing site was chosen carefully, a vast, flat desert in the western United States, the Utah Test and Training Range. This remote location ensured that scientists could quickly recover the capsule and transport it to specialized laboratories. Because once the sample landed, time would become extremely important. The rocks inside had never been exposed to Earth's environment. Scientists wanted to study them before contamination could alter their chemistry. Everything had to be done carefully, with sterile tools, inside sealed laboratories, protected from moisture and air. Only then could researchers begin examining the material from Bennu. And what they would eventually find inside those rocks might help answer one of humanity's oldest questions. How did life begin? But before scientists could unlock those secrets, the capsule first had to complete its long journey home, carrying with it a message from the earliest days of the solar system, a message sealed inside ancient asteroid dust. On September 24th, 2023, after traveling more than 6.2 billion kilometers through space, the OSIRIS-REx mission reached the final and most critical moment of its journey. High above Earth, the spacecraft prepared to release the small capsule carrying Bennu's sample. For years, that capsule had been sealed. Inside it were fragments of rock and dust that had formed before Earth itself was fully assembled. Material older than oceans, older than mountains, possibly older than the moon. At precisely the right moment, the spacecraft released the capsule. Then it fired its engines and moved safely away from Earth, continuing its journey into deep space toward a new mission. But the capsule had only one destination: home. Falling from space, once released, the capsule began its silent fall toward Earth. At first, nothing dramatic happened. It simply drifted through the vacuum of space. But as it approached the atmosphere, everything changed. The capsule was traveling at nearly 44,000 kilometers per hour. At that speed, even the thin upper layers of Earth's atmosphere become incredibly dangerous. As the capsule plunged downward, friction with the air began to heat its surface. Temperatures climbed rapidly. Within seconds, the outer shell was glowing. Soon, it became a streak of fire across the sky. From the ground, observers saw a brilliant meteor-like trail blazing through the early morning darkness. But this was not a natural meteor. It was a carefully engineered spacecraft designed to survive the inferno. The capsule's heat shield protected the precious cargo inside from temperatures hotter than molten lava. As the capsule slowed, the fiery glow gradually faded. Then, at around 33 kilometers above Earth, the next stage began. The parachutes deploy. A small drogue parachute deployed first. Its job was simple: stabilize the capsule and slow it further. Moments later, the main parachute opened. The capsule suddenly transformed from a falling meteor into a drifting object descending gently toward the desert below. Now moving at only a few meters per second, the capsule floated toward the Utah Test and Training Range, a vast military testing area chosen specifically for this mission. Recovery teams were already waiting. Helicopters tracked the descending capsule from the air. Scientists watched nervously as the parachute carried the container closer and closer to the ground. Finally, after 7 years of travel through the solar system, the capsule touched down softly on the desert floor. Inside it were samples of Bennu, untouched pieces of an asteroid older than Earth. For planetary scientists, this moment was historic, but the real work was just beginning. Protecting the sample. The moment the capsule landed, recovery teams moved quickly. Every second mattered. The scientists needed to protect the sample from contamination. Earth's atmosphere contains oxygen, water vapor, bacteria, and countless organic molecules. If those substances mixed with Bennu's material, they could alter the sample and complicate scientific analysis. So the recovery process had been planned down to the smallest detail. Technicians approached the capsule wearing protective gear. Specialized equipment surrounded the landing site. Within minutes, the capsule was carefully secured and placed inside a clean container. Helicopters transported it directly to a temporary clean room facility located nearby. There, engineers inspected the capsule and confirmed that the seal had remained intact. The asteroid sample was safe. Soon after, the container was flown to NASA's Johnson Space Center in Houston, Texas, where a specially designed laboratory awaited. Inside that facility, scientists would finally open the capsule and see material from Bennu for the first time. Opening the container. When the capsule arrived at Johnson Space Center, it was placed inside an advanced clean room. The environment inside the lab was extremely controlled. Air was filtered, humidity levels were carefully regulated, and technicians wore full protective suits to prevent contamination. The capsule itself was transferred into a sealed glove box, a transparent container that allowed scientists to manipulate objects inside using special gloves without exposing the contents to Earth's atmosphere. When the outer container was finally opened, scientists immediately noticed something remarkable. Dust. Black asteroid dust coating the interior surfaces. The sample collector had clearly gathered large amounts of material from Bennu. Some particles had even escaped the sampling head and spread throughout the container during the journey back to Earth. It was the first sign that the mission had collected a truly substantial sample, but the real treasure was still inside the sealed sample head, and opening that device turned out to be more difficult than expected. An unexpected problem. The taxum sampling head had performed perfectly on Bennu. But once the capsule reached Earth, engineers encountered an unexpected challenge. Several fasteners securing the sample head could not be removed with the tools originally planned for the operation. These bolts had been designed to remain secure during the violent re-entry into Earth's atmosphere, and they had done their job extremely well. Too well, in fact. Engineers had to carefully develop new tools that would allow them to safely open the sample head without risking damage to the precious asteroid material inside. The process required patience. Days turned into weeks as technicians worked methodically to access the interior of the container. But eventually, the sampling head was opened, and when scientists finally saw what was inside, they realized the mission had exceeded every expectation. Far more than expected, the OSIRIS-REx mission had been designed to collect at least 60 grams of asteroid material. Anything beyond that would be considered a bonus. When scientists began carefully measuring the contents of the container, the results were astonishing. The mission had returned over 120 grams of material, more than double the required amount, and that number only included the easily accessible portion of the sample. Even more material remained trapped inside the deeper sections of the sampling head. In total, scientists believe the mission may have returned several hundred grams of Bennu's surface, making it the largest extraterrestrial sample returned to Earth since the Apollo moon missions. But what truly excited scientists was not just the quantity, it was the composition. Because the Bennu sample was incredibly rich in carbon. Organic molecules. Early analysis of the sample revealed that Bennu's rocks contain abundant organic compounds. These are molecules built around carbon atoms. Many of them are similar to molecules found in meteorites that have landed on Earth. Some of these compounds include amino acids, the fundamental building blocks of proteins used by living organisms. However, it is important to understand something crucial. Finding organic molecules does not mean scientists found life. These molecules can form naturally in space without any biological processes. But their presence is extremely important because it suggests that the early solar system contained a rich supply of complex organic chemistry. Asteroids like Bennu may have delivered these compounds to Earth billions of years ago. During the early history of the planet, when countless asteroids bombarded the young surface, those impacts may have seeded Earth with the ingredients needed for life to eventually emerge. In other words, Bennu may contain clues about how life began. Water, locked in stone. Another remarkable discovery involved the presence of hydrated minerals inside Bennu's rocks. These minerals form when water interacts with certain types of stone. But Bennu itself has never contained liquid water. Instead, the water interaction must have happened inside the asteroid's much larger parent body billions of years ago. At some point in the distant past, that parent asteroid likely contained ice. Internal heating caused some of that ice to melt, producing liquid water that circulated through the rock. The water altered the minerals, creating the hydrated compounds scientists now see in the Bennu sample. Later, when the parent asteroid was shattered by a massive collision, fragments of those altered rocks eventually reassembled into Bennu. That means Bennu contains pieces of a long-lost ancient world, a world where water once flowed inside rock billions of years ago. Preserving the sample for the future, scientists are being extremely careful with the Bennu material. Only a small portion of the sample will be studied immediately. The majority will remain sealed and preserved for future generations, because scientific technology continues to improve. In the future, researchers may have instruments far more advanced than those available today. By preserving the sample, scientists ensure that decades from now, new discoveries may still be made from the same material. Some of the sample will also be shared with international research institutions, allowing scientists around the world to study Bennu's chemistry and structure. But even with the initial analysis already underway, Bennu is beginning to reveal an extraordinary story, a story that stretches back to the very beginning of the solar system. and perhaps even to the origin of life itself. But the asteroid still holds deeper mysteries, because Bennu is not just an ancient relic drifting through space. It is also a world that continues to change, even today. In the next part, we will explore the strange forces that are slowly reshaping Bennu, and why scientists believe this small asteroid may eventually tear itself apart. Even after the OSIRIS-REx spacecraft left Bennu and began its long journey back to Earth, scientists continued studying the enormous amount of data collected during the mission. And the more researchers examined the asteroid, the clearer one fact became. Bennu is not stable. In fact, the asteroid may be slowly approaching a breaking point because Bennu is spinning, and that rotation is gradually accelerating. A faster and faster spin. When astronomers first measured Bennu's rotation using ground-based telescopes, they discovered that the asteroid completes one full spin roughly every 4.3 hours. That means a day on Bennu is incredibly short. But something strange was happening. The asteroid's spin was not constant. It was slowly increasing. Year after year, Bennu was rotating just a little bit faster. At first, the change seemed tiny, only a small fraction of a second difference over long periods of time. But when scientists compared older telescope observations with new data from OSIRIS-REx, the trend became clear. Bennu's rotation is accelerating by roughly 1 second every 100 years. That may not sound dramatic, but in the long run, it could have serious consequences, because Bennu is not a solid rock. It is a fragile rubble pile, and spinning faster creates powerful forces that can pull that rubble apart. The Sun is responsible. What makes Bennu spin faster is something surprisingly simple. Sunlight. More specifically, the way the asteroid absorbs and re-emits energy from the Sun. This effect is known as the Yorp effect, named after the scientists who helped describe it: Yarkovsky, O'Keefe, Radzievsky, and Paddock. The concept is subtle but powerful. When sunlight strikes the asteroid, the surface absorbs energy and heats up. Later, that heat escapes back into space as infrared radiation. But because Bennu's shape is irregular and uneven, the heat does not leave the surface evenly. Some areas release slightly more energy than others, and that uneven radiation creates a tiny torque, a small twisting force. Each individual push is incredibly weak, but Bennu experiences this process every single day. Over thousands and millions of years, the tiny forces accumulate, gradually changing the asteroid's rotation. OSIRIS-REx confirmed that Bennu's spin is accelerating exactly as predicted by the Yorp effect, which means the Sun is literally spinning the asteroid faster and faster. And if that process continues long enough, Bennu could eventually begin to break apart. Gravity barely holds Bennu together. To understand why Bennu could disintegrate, we need to understand just how weak its gravity actually is. Bennu's mass is extremely small. The entire asteroid weighs roughly 78 billion kilograms. That may sound like a lot, but compared to planets, it is almost nothing. Because of this tiny mass, Bennu's gravitational pull is incredibly weak. If you stood on the asteroid, you would weigh almost nothing. A gentle jump could send you floating away into space. The escape velocity, the speed needed to leave Bennu forever, is only about 20 centimeters per second. That is slower than the speed of a slow walk. A tossed pebble could escape the asteroid completely. This weak gravity is the only force holding Bennu's rubble together. There is no solid core anchoring the asteroid. Instead, thousands of rocks, boulders, and dust particles are loosely bound by gravity and slight friction between the pieces. That fragile balance can be disrupted easily, especially if the asteroid spins too quickly. When asteroids spin too fast, scientists have observed many asteroids that spin extremely rapidly. Some rotate once every few minutes. But these objects are usually solid rocks. A rubble pile like Bennu cannot spin that fast. If Bennu's rotation reaches a critical speed, the outward centrifugal force will overcome gravity. When that happens, material near the equator could begin sliding off the asteroid. Loose rocks could be launched into space. Gradually, Bennu might begin shedding pieces of itself. Eventually, the asteroid could split into multiple fragments. Astronomers have already seen evidence of this process happening elsewhere. Several asteroids have been observed forming binary systems, where a smaller fragment breaks away and begins orbiting the main body. Others have developed long trails of debris stretching through space. These structures are sometimes called active asteroids, objects that slowly lose material as they rotate. Bennu may eventually follow the same path. Evidence on Bennu's surface. Even today, Bennu's surface shows signs that this process may already be happening. The asteroid has a distinctive equatorial ridge, a raised belt of material running around its middle. This ridge likely formed because Bennu's rotation pushed loose rocks toward the equator. Over millions of years, gravity slowly pulled debris downhill from the asteroid's poles toward the equatorial region. There, the spinning motion caused the material to accumulate, creating the distinctive diamond-shaped appearance seen in spacecraft images. But the ridge may also be unstable. If Bennu spins slightly faster, the rocks forming this ridge could begin slipping outward. Some may fall into space. Others might drift away and form small companion asteroids. This process could gradually reshape the asteroid, or eventually destroy it entirely. A lifespan for asteroids. Although asteroids like Bennu may seem permanent, their existence is actually temporary. Over long periods of time, they are constantly evolving. Collisions with other asteroids can shatter them. Solar radiation can change their orbits. Thermal stresses can break apart rocks on their surfaces, and rotation can slowly tear them apart. Scientists estimate that rubble-pile asteroids like Bennu may survive for only tens of millions of years before being destroyed or reshaped by these forces. Compared to the age of the solar system, there is a very short lifespan. But Bennu itself has likely already lived a complex life, because the asteroid is probably not as old as the materials inside it. Younger than its own rocks. The rocks forming Bennu are extremely ancient. Many of them formed more than 4.5 billion years ago, near the birth of the solar system. But Bennu itself may be much younger. Scientists believe the asteroid formed relatively recently, perhaps between 100 million and 1 billion years ago. This happened after the catastrophic collision that destroyed Bennu's parent asteroid. Fragments of that larger object gradually reassembled into smaller rubble-pile bodies. Bennu is one of those fragments. In other words, Bennu is a recycled asteroid, a second-generation object built from the ruins of something much larger. And eventually, Bennu itself may be destroyed in the same way, breaking apart to create new asteroids in the distant future. A cosmic delivery system. While Bennu slowly evolves, it also plays another role in the solar system. It acts as a delivery vehicle. Asteroids like Bennu occasionally collide with planets. And when they do, they bring with them the chemical ingredients locked inside their rocks. During the early history of Earth, billions of asteroids and comets struck the planet. These impacts may have delivered enormous amounts of water. They may also have delivered organic molecules, complex carbon-based compounds capable of forming amino acids, sugars, and other important chemicals. Many scientists believe that these materials helped create the conditions necessary for life to begin on Earth. If that idea is correct, then objects like Bennu may have helped make life possible. The asteroid itself may never host life, but it may carry the ingredients needed to create it. A window into the past. This is why Bennu is so important to scientists. It is not just an asteroid drifting through space. It is a preserved archive of the early solar system. Inside its rocks are chemical records billions of years old. Records that may reveal how water spread through the young solar system, how organic molecules formed in space, and how those molecules eventually reached Earth. Studying Bennu's sample in laboratories on Earth allows scientists to analyze these materials with incredible precision. They can examine the structure of the minerals, identify individual molecules, and even determine the temperatures and environments in which those materials formed. Each discovery adds another piece to the puzzle of our origins. But Bennu also reminds us of something else. The solar system is not static. It is constantly changing. Asteroids collide, planets shift, small worlds like Bennu evolve and eventually disappear. Yet even as Bennu slowly drifts through space, spinning faster with each passing century, it has already delivered one of the most valuable scientific treasures humanity has ever received. A handful of ancient dust, carrying the story of the solar system's beginning. When the Bennu sample finally arrived inside NASA's laboratories, scientists knew they were looking at something extraordinary. These rocks were not just fragments of an asteroid. They were pieces of the earliest solar system, material that had remained almost completely unchanged for more than 4.5 billion years. On Earth, geological processes constantly reshape the planet. Plate tectonics recycle the crust. Volcanoes melt and reform rock. Water erodes mountains and deposits sediments. Even meteorites that land on Earth quickly begin to react with air and moisture. But Bennu's rocks had spent billions of years drifting through the vacuum of space. Cold, dry, preserved. That makes them incredibly valuable to scientists, because they provide a direct glimpse into the chemistry that existed when the planets were still forming. And the first analyses of the Bennu sample quickly revealed something remarkable. The asteroid is rich in carbon. A carbon-rich asteroid carbon is one of the most important elements in the universe. It forms the backbone of nearly every molecule used by living organisms. Proteins, sugars, DNA, all rely on complex chains of carbon atoms. But carbon is also extremely common in space. Many asteroids contain carbon-bearing minerals and organic molecules. Bennu belongs to a class known as carbonaceous asteroids, sometimes called C-type asteroids. These objects are among the most primitive bodies in the solar system. They formed early and avoided the intense heating that reshaped many other asteroids. Because of this, they preserve ancient materials from the solar system's formation. When scientists began studying Bennu's sample, they found exactly what they hoped for: large amounts of carbon-rich compounds embedded in the rock. Some of these compounds are simple organic molecules. Others are far more complex. Together, they paint a picture of a solar system filled with chemical activity, even before planets fully formed. Organic chemistry in space. The word organic can sometimes cause confusion. In everyday language, it often refers to life, but in chemistry, organic molecules simply contain carbon. They can form naturally in many environments, including outer space. In fact, complex organic molecules have been detected in interstellar clouds between stars. They form through chemical reactions driven by radiation, heat, and cosmic particles. When the solar system formed from one of these clouds of gas and dust, many of those organic compounds were already present. Some became trapped inside comets and asteroids. Over billions of years, those objects preserve the chemistry of that ancient environment. The Bennu sample confirms that this process was widespread. Scientists analyzing the asteroid material have identified numerous carbon-based molecules. Some resemble compounds previously found in meteorites. Others may be entirely new. But perhaps the most exciting discovery involves molecules known as amino acids. The building blocks of proteins. Amino acids are essential to life as we know it. They are the building blocks of proteins, the molecules that perform countless functions inside living cells. Proteins allow organisms to grow, repair tissue, and carry out chemical reactions. Finding amino acids in an asteroid does not mean life existed there, but it does demonstrate that the ingredients needed to build proteins can form naturally in space. Scientists have already detected amino acids in several meteorites that fell to Earth. But the Bennu sample provides something even more valuable: a pristine sample collected directly from an asteroid, untouched by Earth's environment. This eliminates many uncertainties about contamination. The presence of amino acids in Bennu suggests that the early solar system contained large amounts of these molecules. Asteroids and comets may have delivered them to the young Earth billions of years ago, and that delivery may have helped create the conditions necessary for life to emerge. Water hidden in minerals. Along with organic molecules, Bennu's sample also contains strong evidence of water. Not liquid water, but water trapped inside minerals. Scientists call these hydrated minerals. They form when water chemically reacts with rock. Water molecules become incorporated into the crystal structures of minerals, remaining there even after the liquid water disappears. These minerals tell scientists something important about Bennu's history. At some point in the distant past, the rocks that now make up Bennu were exposed to liquid water, but Bennu itself is far too small to support liquid water internally. Instead, the water interaction must have occurred inside Bennu's parent asteroid billions of years ago. That larger body likely contained significant amounts of ice. When internal heating occurred, perhaps from radioactive decay, some of that ice melted. The liquid water flowed through cracks and pores in the rock. Chemical reactions transformed the minerals. Eventually, the parent asteroid was shattered by a massive collision. Fragments of those altered rocks eventually reassembled into Bennu, which means Bennu contains pieces of a much larger ancient world that once contained liquid water. A chemical time capsule. The Bennu sample is often described as a time capsule. That description is not an exaggeration. Inside the asteroid material are chemical signatures preserved from the earliest stages of planetary formation. These signatures help scientists answer important questions about the solar system's origins. For example, what kinds of organic molecules existed before the planets formed? How common was water in the early solar system? What chemical reactions occurred inside early asteroids? And how were these materials distributed across the young solar system? By studying Bennu's rocks, scientists can reconstruct events that happened billions of years ago, events that shaped the formation of Earth and the other planets. Each grain of dust inside the sample carries information about those ancient processes. Isotopes and cosmic history. One of the most powerful tools scientists use when studying asteroid samples is isotope analysis. Atoms of the same element can exist in slightly different forms called isotopes. These isotopes have the same number of protons but different numbers of neutrons. Because of this, their masses are slightly different. Certain processes in space leave distinctive isotope signatures in materials. By measuring these signatures, scientists can determine where and when the material formed. For example, some isotopes indicate formation in extremely cold environments. Others suggest exposure to intense radiation. Using isotope analysis, researchers can trace Bennu's material back to the early solar nebula, the cloud of gas and dust that eventually formed the sun and planets. This allows scientists to study the conditions that existed during the solar system's birth. In many ways, Bennu provides a laboratory for studying events that occurred long before Earth even existed. Tiny grains, older than the sun. Within the Bennu sample, scientists may eventually find something even more extraordinary. Tiny grains of material older than the solar system itself. These are known as pre-solar grains. They formed around ancient stars that existed before our sun was born. When those stars died, they expelled material into space. That material later became part of the cloud that formed our solar system. Some of those grains survived the entire process, from ancient star to interstellar cloud to asteroid, and finally to Earth. Finding pre-solar grains in Bennu's sample would provide a direct link to stellar processes that occurred billions of years before our sun formed. Essentially, fragments of ancient stars embedded inside asteroid dust. A shared treasure. The Bennu sample is not being studied by NASA alone. Scientists around the world are participating in the research. Small portions of the sample are being distributed to research institutions in multiple countries. Each laboratory specializes in different analytical techniques. Some focus on organic chemistry. Others analyze mineral structures. Some examine isotopes. Others study microscopic structures within the rocks. By combining results from many different scientific fields, researchers can build a comprehensive understanding of Bennu's composition and history. And this process may continue for decades, just as samples from the Apollo moon missions are still producing new discoveries today. A message. From the beginning, Bennu may be small, only half a kilometer wide, yet it carries within it a story that stretches back to the birth of the solar system. A story written in carbon molecules, in hydrated minerals, in ancient dust older than the Earth itself. The OSIRIS-REx mission has delivered that story directly into the hands of scientists. But unlocking all its secrets will take time, because each grain of Bennu's dust contains layers of information waiting to be understood. Information about the chemistry that preceded life, about the environments that shaped the earliest asteroids, and about the ancient processes that built the planets we know today. Bennu may look like a simple pile of rubble drifting through space, but inside that rubble lies a record of the universe's past. A record that scientists are only beginning to read. Although Bennu has revealed remarkable secrets about the early solar system, the asteroid also represents something else, a reminder that space is not empty. The solar system is filled with millions of rocky bodies drifting through space. Most remain safely distant from Earth, but some follow paths that occasionally cross our planet's orbit. These are known as near-Earth asteroids. Bennu belongs to this group, and that fact alone makes it extremely important, because studying Bennu is not only about understanding the past, it is also about protecting the future. Tracking dangerous asteroids, astronomers around the world constantly search the sky for near-Earth asteroids. Powerful telescopes scan the darkness every night, looking for objects that move slowly against the background of stars. When a new asteroid is discovered, scientists immediately begin calculating its orbit. They determine how the object moves around the Sun and whether it might approach Earth in the future. Most asteroids pose no threat. Their paths remain safely distant from our planet. But occasionally, an asteroid appears whose orbit crosses Earth's path. These objects require closer monitoring, because even a small asteroid impact could cause serious damage. Large impacts, although extremely rare, could have global consequences. This is why planetary scientists carefully study asteroids like Bennu. Understanding their structure, composition, and behavior helps scientists prepare for any potential threat. Bennu's orbit. Bennu travels around the Sun once every 436 days. Its orbit lies mostly between the paths of Earth and Mars. During part of its journey, the asteroid passes relatively close to Earth, close enough that our planet's gravity can slightly influence its motion. Each close approach alters Bennu's orbit just a little. Over long periods of time, those tiny gravitational nudges make predicting the asteroid's path extremely complex. Scientists use powerful computers to simulate Bennu's orbit far into the future. These simulations include every gravitational influence in the solar system: the Sun, the planets, even the pressure of sunlight. All of these forces slowly shape the asteroid's trajectory. The results show that Bennu will make several relatively close passes by Earth during the next 2 centuries, and one of those future encounters has received particular attention. The year 21 82. According to current calculations, Bennu's most significant potential close approach occurs on September 24, 2182. During that encounter, the asteroid will pass extremely close to Earth's orbit. The probability of an actual impact is very small, only about 1 in 2,700. That means there is more than a 99.96% chance that Bennu will safely miss our planet. Still, Bennu remains one of the most carefully tracked asteroids in the solar system. Because even small uncertainties in its orbit can change predictions over long periods of time, and Bennu's path is influenced by more than just gravity. Another subtle force plays an important role: the Yarkovsky effect. Earlier we discussed the Yorp effect, which slowly changes Bennu's rotation. But sunlight influences asteroids in another way as well. This is known as the Yarkovsky effect. When sunlight heats an asteroid surface, that heat is later released as infrared radiation. As the asteroid rotates, the warmest region shifts slightly toward the afternoon side. The emitted heat acts like a tiny thrust, a gentle push. This force is extremely weak, but it acts continuously for millions of years. Over time, it can slowly change an asteroid's orbit. For Bennu, the Yarkovsky effect causes the orbit to drift gradually. OSIRIS-REx measured this drift directly during its time at the asteroid. By tracking the spacecraft's position relative to Bennu with incredible precision, scientists were able to calculate the asteroid's motion more accurately than ever before. This improved data significantly reduced uncertainties about Bennu's future path. Thanks to these measurements, astronomers now have one of the most precise asteroid orbit predictions ever calculated, and the news is reassuring. Bennu is extremely unlikely to strike Earth anytime soon. Why studying Bennu matters. Even though the chance of Bennu impacting Earth is very small, studying the asteroid provides invaluable knowledge. Because someday another asteroid might pose a real threat. If that happens, scientists must know how to respond. And the first step in defending Earth from an asteroid is understanding the asteroid itself. Different asteroids behave in very different ways. Some are solid rock. Others are loose rubble piles like Bennu. Some contain metal. Others contain carbon-rich minerals. These differences matter because any attempt to deflect an asteroid must account for its internal structure. If an asteroid is solid, pushing it slightly might alter its orbit. But if the asteroid is loosely held together, a strong impact could break it into fragments. Those fragments might still remain on a collision course with Earth. Studying Bennu helps scientists understand how rubble-pile asteroids respond to external forces. Testing planetary defense. In recent years, scientists have begun testing real techniques for asteroid deflection. One example is NASA's DART mission. In 2022, the DART spacecraft intentionally collided with a small asteroid moon called Dimorphos. The impact slightly altered the moon's orbit around its parent asteroid, Didymos. This experiment demonstrated that kinetic impacts can change the motion of an asteroid, but the response of each asteroid may differ depending on its structure. Observations from OSIRIS-REx suggest that Bennu's surface behaves almost like loose sand. When the spacecraft touched the asteroid, it sank deeply into the material. That means Bennu is extremely porous. An impact on such an object might behave very differently compared to striking solid rock. Understanding these differences is essential for designing future planetary defense missions. Bennu as a natural laboratory. Because Bennu is relatively accessible and well studied, it serves as a perfect natural laboratory. Scientists can test models of asteroid physics using real data collected during the OSIRIS-REx mission. They can study how sunlight changes asteroid rotation, how rubble piles respond to forces, how surface materials move across low-gravity environments. These insights improve our ability to predict how other asteroids behave, which means Bennu is not just a scientific curiosity. It is also helping humanity prepare for future challenges. The long-term fate of Bennu. Even without human intervention, Bennu's future is uncertain. Over millions of years, gravitational interactions with planets will gradually reshape the asteroid's orbit. Eventually, Bennu may experience a close encounter with Earth or another planet that dramatically alters its trajectory. One possible outcome is that Bennu could be ejected from the inner solar system. Another possibility is that it could collide with a planet, or perhaps with the Sun itself. But there is another scenario as well, because Bennu may not survive long enough for any of those outcomes. A fragile world. As we explored earlier, Bennu is a rubble-pile asteroid barely held together by gravity. Its rotation is slowly increasing due to the YORP effect. If the spin becomes too fast, the asteroid could begin losing material. Rocks might drift away from the surface. Fragments could break off and form new asteroids. Eventually, Bennu could completely disintegrate, breaking apart into a cloud of smaller objects. If that happens, the pieces may follow slightly different orbits around the Sun. Some fragments might drift harmlessly through space. Others could eventually enter Earth-crossing paths. In that sense, Bennu represents a transitional stage in the life cycle of asteroids, a temporary structure that will eventually evolve into something else. Lessons from Bennu. The OSIRIS-REx mission has transformed our understanding of small asteroids. Before visiting Bennu, scientists knew relatively little about how rubble-pile asteroids behaved. Now we know they can eject particles into space. We know their surfaces may behave like fluidized sand. We know sunlight can slowly reshape their rotation. And we know they may contain complex organic chemistry dating back billions of years. All of these discoveries came from studying a world barely half a kilometer wide, a tiny fragment of the solar system. Yet Bennu has provided enormous insight into planetary science. And the story is not finished. Because the asteroid sample returned to Earth will continue revealing new secrets for decades. Every grain of dust carries information about ancient cosmic events. Events that shaped the formation of planets. Events that may have helped create life itself. But Bennu's story also reminds us of something humbling. The solar system is filled with countless small worlds, each with its own history, each carrying pieces of the universe's past. And sometimes, one of those worlds drifts close enough for us to reach it, to study it, and to learn something new about where we came from. In the next part, we will explore what scientists hope to discover next from Bennu's ancient material, and how these discoveries may reshape our understanding of the origins of life in the universe. When scientists finally began analyzing the material returned from Bennu, they were not just studying an asteroid, they were studying the ingredients that may have helped create life itself. Because long before Earth became a blue world covered in oceans, the young planet experienced an era of violent bombardment. Billions of asteroids and comets slammed into its surface. Each impact delivered enormous amounts of rock, ice, and chemical compounds. Among those materials may have been the very molecules that later became part of living organisms, and Bennu might represent one of the best preserved examples of those ancient deliveries. Earth's violent beginning. About 4.5 billion years ago, the Earth was a very different place. The surface was molten. Volcanoes erupted constantly. The atmosphere was thick with gases released from the planet's interior. At the same time, the early solar system was filled with leftover debris from planet formation. Asteroids and comets traveled through chaotic orbits. Collisions between these bodies were common. Many of them struck the young Earth. This period is known as the Late Heavy Bombardment. Although the exact timing remains debated, scientists know that countless impacts occurred during the first several 100 million years of Earth's history. Each asteroid carried material from other parts of the solar system: water, carbon compounds, complex molecules. These impacts may have played a crucial role in shaping Earth's environment, and possibly in creating the conditions needed for life to begin. Asteroids as chemical carriers. Asteroids like Bennu are not simply lumps of rock. They are chemically complex worlds. Within their minerals and dust are countless organic molecules. Many of these compounds formed naturally in space through chemical reactions driven by radiation and energy from nearby stars. When the solar system formed, these molecules became incorporated into asteroids and comets. Over time, impacts delivered them to planets. This process may have provided Earth with a rich supply of organic chemistry. Some researchers believe that amino acids and other important molecules may have arrived this way. Others suggest that asteroid impacts also delivered large amounts of water. If these ideas are correct, asteroids may have played a direct role in the origin of life on Earth. Studying Bennu helps scientists test these theories. A laboratory on Earth. One of the greatest advantages of the OSIRIS-REx mission is that scientists can study the Bennu sample using instruments far more advanced than anything that could be carried on a spacecraft. Inside laboratories, researchers can examine the material at microscopic scales. Some grains of Bennu's dust are smaller than a human hair, yet inside those grains are complex chemical structures. Scientists use powerful microscopes and spectrometers to analyze the composition of each particle. They measure the arrangement of atoms within minerals. They identify organic molecules trapped inside microscopic pores. And they carefully record every chemical signature preserved within the sample. These analyses allow scientists to reconstruct the conditions under which Bennu's materials formed. In some cases, researchers can determine temperatures, chemical environments, and even the presence of ancient water interactions billions of years ago. Organic molecules and prebiotic chemistry. Among the most fascinating discoveries in asteroid samples are compounds related to prebiotic chemistry. Prebiotic chemistry refers to the chemical processes that occur before life begins. These reactions can produce molecules that later become part of living systems. In meteorites that have fallen to Earth, scientists have already identified dozens of amino acids. Some of these molecules are rare or absent in living organisms. This suggests they formed naturally in space rather than through biological activity. If Bennu contains similar molecules, it would strengthen the idea that complex chemistry existed widely throughout the early solar system. In that case, the building blocks of life may not be rare. They may be common throughout the universe. Water and habitability. Water is another crucial ingredient for life. Every known living organism depends on it. Understanding how Earth obtained its water remains one of the most important questions in planetary science. Early theories suggested that water was delivered primarily by comets. However, more recent research indicates that many asteroids also contain large amounts of water-bearing minerals. Bennu's sample supports this idea. The presence of hydrated minerals indicates that water once interacted with the asteroid's parent body. This suggests that water-rich asteroids were common in the early solar system. If such objects frequently collided with the young Earth, they could have delivered significant amounts of water to the planet's surface. Over time, these contributions may have helped form Earth's oceans. A universal process? One of the most intriguing implications of the Bennu sample involves the possibility that the chemistry leading to life may occur naturally in many places throughout the universe. If organic molecules and water are common in asteroids, then similar materials likely exist in other planetary systems. Around other stars, countless asteroids and comets probably form during planet formation. These objects may carry the same types of organic molecules found in Bennu. If those asteroids collide with young planets elsewhere, they could deliver similar ingredients. This means the processes that helped create life on Earth might not be unique. They might happen anywhere the right conditions exist. Studying Bennu helps scientists understand whether the chemical foundations of life are rare or widespread. Searching for complexity, researchers are now examining Bennu's material for increasingly complex molecules. Simple organic compounds are relatively common. But more complicated molecules, those with larger structures and multiple chemical groups, could reveal much more about early solar system chemistry. Scientists are particularly interested in molecules related to sugars, nucleic acids, and other compounds involved in biological processes. Even if these molecules formed naturally without life, their presence would demonstrate that complex chemistry can arise in space. And that could mean the steps toward life begin long before planets themselves become habitable. A window into early planetary systems. Beyond chemistry, Bennu also provides insight into the physical processes that shaped early planetary systems. The asteroid formed from fragments of a larger body that once experienced water alteration. That parent asteroid likely formed farther out in the solar system, where temperatures were low enough for ice to exist. Later, gravitational interactions and collisions scattered fragments inward. Eventually, some of those fragments entered near-Earth orbits. Studying Bennu allows scientists to trace this history. By analyzing mineral structures and isotopic signatures, researchers can determine where the materials originally formed. This helps reconstruct the movement of objects through the early solar system, and it reveals how materials were distributed among the forming planets. A story, written in dust. Every grain of Bennu's sample tells part of this story. Microscopic crystals record chemical reactions that occurred billions of years ago. Organic molecules reveal how carbon-based chemistry developed in space. Hydrated minerals show where water once flowed through rock. Together, these clues allow scientists to piece together a timeline of events stretching back to the birth of the solar system. Few scientific discoveries offer such a direct connection to our origins. Most geological records on Earth have been altered or destroyed over time, but Bennu's rocks have remained largely unchanged since their formation. They are a snapshot of the early solar system preserved in asteroid dust. The beginning of a long investigation. Although the Bennu sample has already produced exciting discoveries, the investigation has only just begun. Scientists expect to study the material for decades. New technologies will allow future researchers to analyze the sample in ways that are impossible today. Just as Apollo moon samples continue to produce new insights more than 50 years after they were collected, Bennu's material will likely remain valuable far into the future, and every new discovery will deepen our understanding of the solar system's origins. But Bennu also raises new questions. Questions about how common organic chemistry is throughout the universe, about how water and carbon compounds spread across planetary systems, and about how often those ingredients combine to create life. In the next part, we will explore what scientists still hope to learn from Bennu, and why this tiny asteroid may influence the future of space exploration itself. Although Bennu is only about half a kilometer wide, the asteroid may help answer questions that extend far beyond the origin of life. It may also help humanity prepare for the future, because as space exploration advances, asteroids like Bennu may become extremely valuable, not just scientifically, but economically, and even strategically. These small worlds could eventually become stepping stones for human activity in space. The resources hidden in asteroids. Asteroids contain a wide variety of materials. Some are rich in metals, such as iron and nickel. Others contain rare elements used in advanced technologies. Still others, like Bennu, contain large amounts of carbon compounds and water-bearing minerals. Water is one of the most valuable resources in space, not only because humans need it for survival, but because water can also be separated into hydrogen and oxygen. Hydrogen can be used as rocket fuel. Oxygen can support breathing and combustion. This means that water-rich asteroids could eventually serve as natural fuel stations for spacecraft. Instead of launching all fuel from Earth, which is extremely expensive, future missions might obtain resources directly from asteroids. This idea is known as in situ resource utilization, or ISRU, and Bennu may represent the kind of asteroid that could support such operations. Mining the solar system. The concept of asteroid mining has been discussed for decades. The idea is simple. asteroids contain enormous amounts of valuable materials. Some metallic asteroids may contain more platinum, nickel, and other rare metals than exist in Earth's crust. Others contain water ice that could support long-duration space missions. Although asteroid mining remains technologically challenging, it is becoming increasingly realistic. Robotic spacecraft could one day extract materials from asteroids and transport them to orbital facilities. Those materials might then be used to build spacecraft, satellites, or even large structures in space. Because launching materials from Earth requires enormous energy, but resources already in space can be used much more efficiently. Asteroids like Bennu offer a glimpse of what those future resource targets might look like. Learning how to work on asteroids. Before humans can ever mine or utilize asteroid resources, scientists must understand how these objects behave. And Bennu has already revealed something crucial. Its surface is incredibly fragile. When the OSIRIS-REx spacecraft touched the asteroid, it sank deeply into the loose regolith. The ground behaved almost like a fluid. Rocks shifted and dust erupted outward. This discovery shows that working on a rubble-pile asteroid may be very different from operating on solid ground. Machines designed to drill or excavate material must account for extremely low gravity and unstable surfaces. Even simple movements could send equipment drifting away from the asteroid. Understanding these challenges now will help engineers design future missions capable of safely interacting with small bodies. The low-gravity environment. Bennu's gravity is roughly 100,000 times weaker than Earth's. In such an environment, traditional construction or mining techniques would not work. Heavy equipment would weigh almost nothing. Even small forces could move large objects. Dust and debris might float away easily. For astronauts or robotic systems, maintaining contact with the surface would require specialized tools, anchors, harpoons, tethers. All of these ideas have been proposed for working on small asteroids. Studying Bennu helps scientists understand how these techniques might function in real conditions. Asteroids as waypoints. In the distant future, asteroids may also serve as stopping points for deep space missions. Instead of traveling directly from Earth to Mars or beyond, spacecraft might stop at asteroids along the way. There, they could refuel using extracted water or other resources. Asteroids might also provide raw materials for building structures in space, radiation shielding, habitat walls, or even entire space stations. Some researchers have proposed hollowing out large asteroids to create natural shelters for astronauts. The thick rock would provide protection from cosmic radiation and micrometeoroids. While such ideas remain speculative, they illustrate the potential importance of asteroids in humanity's long-term presence in space. Bennu's scientific legacy. Even without mining operations or future settlements, Bennu has already secured its place in the history of space exploration. The OSIRIS-REx mission demonstrated that it is possible to travel to a distant asteroid, collect material, and return it safely to Earth. This achievement required extraordinary precision. The spacecraft navigated through an environment with almost no gravity, mapped the asteroid in detail, selected a safe sampling site, and successfully returned material from a world hundreds of millions of kilometers away. Few missions have ever accomplished such a complex series of tasks The knowledge gained from OSIRIS-REx will influence future asteroid missions for decades. A continuing journey. Although the OSIRIS-REx spacecraft completed its primary mission when it delivered Bennu's sample to Earth, the spacecraft itself did not retire. After releasing the sample capsule in 2023, the spacecraft continued traveling through space. NASA assigned it a new mission. The spacecraft was renamed OSIRIS-APEX. Its next destination is another near-Earth asteroid called Apophis. Apophis will pass extremely close to Earth in 2029. During that encounter, the asteroid will come closer than many satellites orbiting our planet. The OSIRIS-APEX spacecraft will study Apophis during this close approach, observing how Earth's gravity alters the asteroid's surface and structure. This mission will provide valuable data about how asteroids respond to strong gravitational interactions. Once again, Bennu's mission is helping scientists prepare for future discoveries. A tiny world with enormous impact. At first glance, Bennu may seem insignificant, a dark, rocky object drifting silently through space. But this small asteroid has changed our understanding of the solar system. It has revealed how rubble-pile asteroids behave, how sunlight can slowly reshape their rotation, how ancient water and organic molecules may be preserved within their rocks, and how these materials may have helped create the conditions for life on Earth. It has also provided practical knowledge for future asteroid missions. Knowledge that may one day protect our planet or help humanity expand beyond it. A connection across time. Perhaps the most remarkable aspect of Bennu is the connection it provides between the past and the future. The asteroid formed from material billions of years old. Dust that existed before Earth became the planet we know today. Yet those same rocks are now helping scientists understand how humanity might one day explore the solar system. A tiny world carrying a story that spans the entire history of our planetary neighborhood, from the birth of the sun to the origin of life to the future of space exploration, and all of it contained within a handful of ancient dust returned to Earth from a distant asteroid. In the final part, we will explore what Bennu ultimately teaches us about the solar system itself and why this small asteroid may represent one of the most important discoveries of modern planetary science. When the capsule carrying Bennu's sample finally landed on Earth, it marked the end of one journey, but it also marked the beginning of another. Because the true mission of Bennu was never just about visiting an asteroid. It was about understanding our place in the universe. Inside that small container of dark dust and stone lies a message that has been traveling through space for billions of years, a message from the earliest days of the solar system. A time capsule. From the beginning, most rocks on Earth cannot preserve a perfect record of the planet's early history. Over billions of years, our planet has been reshaped by tectonic activity, erosion, volcanoes, and weather. Mountains rise and disappear. Oceans open and close. Even entire continents drift across the surface. These processes constantly recycle Earth's crust. As a result, very little material from the earliest history of the solar system still exists on our planet. But asteroids like Bennu are different. They are far smaller than planets. They never developed active geology, no plate tectonics, no oceans, no atmosphere to erode their surfaces. For billions of years, many asteroids have remained almost unchanged. That means their rocks preserve a record from a time long before Earth's surface stabilized. They are natural time capsules, and Bennu is one of the best preserved among them. The birth of the solar system. To understand Bennu's significance, we must go back more than 4.5 billion years. At that time, the solar system did not yet exist. Instead, there was a vast cloud of gas and dust drifting through space. This cloud, known as the solar nebula, contained the raw materials that would eventually form the Sun, the planets, and countless smaller bodies. At some point, gravity began pulling this cloud inward. As it collapsed, the center became denser and hotter. Eventually, nuclear fusion ignited. The Sun was born. Around the young star, the remaining gas and dust flattened into a rotating disk. Within that disk, tiny particles began colliding and sticking together. Dust became pebbles. Pebbles became rocks. Rocks combined into larger bodies known as planetesimals. Some of these objects eventually grew into planets. Others remained small and scattered throughout the solar system. Asteroids like Bennu are survivors from that chaotic era. They contain materials that formed before the planets were fully assembled. The ancient parent body scientists believe Bennu did not form as an isolated object. Instead, it likely originated as part of a much larger asteroid. This parent body may have been tens or even hundreds of kilometers wide. Inside that larger asteroid, heat generated by radioactive elements warmed the interior. Ice melted, liquid water flowed through cracks in the rock. Chemical reactions transformed minerals and created hydrated compounds. These reactions also produced organic molecules. Eventually, the parent asteroid experienced catastrophic collisions. Fragments were scattered across the solar system. Some of those fragments later reassembled under their own weak gravity. Over time, they formed rubble-pile asteroids like Bennu. In this sense, Bennu is not a single rock. It is a collection of many ancient fragments. Each piece carries a record of different events from the early solar system. Reading the chemical record. When scientists analyze Bennu samples, they examine not only what the material contains, but also how those materials formed. For example, the arrangement of atoms inside minerals can reveal the temperatures at which the minerals crystallized. Isotopes, different forms of the same element, can reveal where the material originated. Some isotopes form only under specific conditions. Others may indicate whether water once interacted with the rock. By studying these chemical signatures, researchers can reconstruct the environment in which Bennu's materials formed billions of years ago. It is like reading a geological diary written in stone. Every mineral layer, every chemical compound, records a chapter in the history of the solar system. A fragile world. One of the most surprising discoveries about Bennu is how fragile it is. The asteroid is not a solid monolithic rock. Instead, it is loosely held together by gravity. Boulders, pebbles, and dust are piled together into a rubble structure. Between these fragments are empty spaces. In some ways, Bennu resembles a floating pile of debris. This structure explains why the OSIRIS-REx spacecraft sank so deeply into the surface when it attempted to collect its sample. The ground simply gave way beneath it. Understanding this structure is extremely important because many near-Earth asteroids appear to share this rubble-pile composition, and that has major implications for planetary defense. Protecting Earth from asteroids. Bennu itself is classified as a potentially hazardous asteroid. Its orbit brings it close to Earth roughly every 6 years. Although the probability of impact is extremely small, scientists continue to monitor its trajectory carefully. Asteroids like Bennu remind us that Earth exists within a dynamic cosmic environment. Collisions between planets and asteroids have occurred throughout the history of the solar system. Some impacts have been catastrophic. The asteroid that struck Earth 66 million years ago is believed to have contributed to the extinction of the dinosaurs. Understanding the structure of asteroids like Bennu helps scientists develop strategies to prevent similar events in the future. If a threatening asteroid were ever discovered on a collision course with Earth, we might attempt to deflect it. But the success of such a mission would depend on understanding how the asteroid structure responds to force. A solid rock would behave differently from a loose rubble pile. Bennu provides critical data that helps scientists prepare for such scenarios. Lessons from a small world. What makes Bennu so remarkable is that such a small object can answer such enormous questions. It tells us about the earliest chemistry of the solar system, about the role asteroids may have played in delivering water and organic molecules to Earth, about the structure and behavior of rubble-pile asteroids, and about the potential resources available in small bodies throughout the solar system. Few space missions have produced such a wide range of scientific insights, and yet the Bennu sample represents only a tiny fraction of the asteroid itself. Most of Bennu still drifts silently through space, a small world carrying billions of years of history. The long future of Bennu's sample. NASA has preserved much of Bennu's sample for future generations of scientists. Only a portion will be studied immediately. The rest will remain sealed and protected. This approach allows future researchers, using technologies that do not yet exist, to analyze the material in new ways. This strategy proved incredibly successful with the Apollo moon samples. Decades after astronauts brought those rocks back to Earth, scientists continued to make new discoveries using improved instruments. The Bennu sample will likely follow the same path. For the next 50 or even 100 years, scientists will continue uncovering new secrets from this ancient asteroid. A quiet messenger. Perhaps the most poetic aspect of Bennu is the idea that this asteroid has been traveling through space long before humanity existed. For billions of years, it drifted around the sun, silent, unnoticed, carrying within it the chemical story of the solar system's birth. Then, for the first time in its history, intelligent beings reached out and touched it, collected a piece of its surface, and brought that piece home. In doing so, humanity opened a window into a time long before our planet even had oceans, before continents formed, before life existed at all. The story Bennu tells us that the universe is filled with ancient material that formed before planets, before life, before Earth itself became habitable. It tells us that the ingredients of life may be common, scattered throughout asteroids and comets across the cosmos. It tells us that small worlds drifting through space may hold answers to some of humanity's biggest questions. Where did we come from? How did life begin? And how common might life be in the universe? All of those questions may begin with something as small as a grain of dust from an asteroid. A message from the dawn of time. Bennu is not just an asteroid. It is a messenger, a fragment of the ancient solar system that has traveled billions of years to reach us. And within its dark rocks lies a record of cosmic history, a story written long before humans existed, a story we are only beginning to understand. And as scientists continue studying the material Bennu delivered to Earth, that story will continue unfolding, revealing new secrets, new mysteries, and perhaps even new insights into how life itself began. Because sometimes the smallest worlds carry the biggest answers. And Bennu may be one of the most important messengers the universe has ever sent